Audio recording for this meeting has begun.
So again, good morning and good afternoon, everybody, and welcome to today's NICR webcast. Today's presentation is entitled The Congestion Evaluation and Mitigation for Urban Parcel Delivery. Let me tell you a little bit about our two presenters today before I hand the time over to them. Our first presenter today will be Mark Hansen. Mark is a professor of civil and environmental engineering at the University of California, Berkeley. He graduated from Yale with a bachelor's degree in physics and philosophy in 1980 and has a PhD in engineering science and a master's degree in city and regional planning from UC Berkeley. He joined the Berkeley faculty in 1988 and has led the transportation research projects in urban transportation planning, air transport systems modeling, air traffic flow management, aviation systems performance analysis, aviation safety, aviation environmental analysis, and air transport economics. Our second presenter today will be Ange Lee. Ange is a fourth-year doctoral student and is advised by Professor Mark Hansen in the Transportation Engineering Department at UC Berkeley. Her research interests focus on unmanned aircraft systems, traffic management, and regional air traffic management using operation research and machine learning techniques. With that being said, I'm going to hand the presentation over to Mark. So Mark, I'm going to unmute you and take it away.
Hi, Stephanie. Can you still hear me okay?
Yes, I can.
All right. Good morning, everyone. Morning to us here on the West Coast. And thank you, Stephanie, and your colleagues at USF for both arranging for this webinar and also for all of your efforts in NICR, which makes it a nicer center for all of us. So the work that I'm going to be speaking about today was kind of born a couple of years ago, and it was actually the topic was of interest to us well before the pandemic, but has gained kind of a new salience during the pandemic. And as the title says, it concerns looking at congestion issues around urban parcel delivery. I should say that the work that I'm presenting here is one piece of a larger effort that also includes colleagues at South Florida, particularly a group led by Pei-Sung Lee, who is looking at safety aspects of this same urban parcel issue. And so let me start the presentation. So the first part of this is going to just kind of look at the landscape of e-commerce and document the fact that e-commerce has become an increasingly important part of the U.S. and world economies. So the chart here is looking at the total amount of both online and offline sales. And the percentages that you see are the percentages that are online sales, which would normally involve a last mile delivery, which will be the focus here. And you can see that consistently the share of the orange online sales piece has been going up since 2012, and that it had a major jump in 2020, where there was a actual reduction in offline retail for reasons related to the pandemic. There have been somewhat of a rebound from that, but we can see that even in 2021, the share of online is substantially more than it was in the pre-pandemic period. And another way to look at this is just in terms of, I didn't mean to do that, excuse me. Another way to look at this is just in terms of the percentage growth in e-commerce sales. And so that growth was quite steady and quite large, on the order of 10, 11% pre-pandemic year over year, and then jumped in the pandemic period to a much greater growth. And that growth has kind of settled down, but as we saw before, there's still a substantial kind of residual effect of the pandemic in terms of increasing the e-commerce share of total retail sales. So this is, so far we've just kind of looked at the recent past, but what are people saying about the future? And what people are saying about the future is that there will be continued demand, increased demand for last mile delivery. One study suggested that between 2019 and 2030, there'll be a 78% increase in last mile delivery activity. And some of the reasons here include just greater urbanization, greater penetration of online shopping in that urban population. Particular example being, for example, groceries that are increasingly an online product. There is also expected to be greater demand for not just delivered goods, but rapidly delivered goods, so same-day delivery. And one of the implications of this that is getting interest is the use of more advanced vehicles, including potentially automated vehicles to provide this delivery. Why, besides the obvious circumstances of COVID, why do people want more last mile deliveries? Why is the market shifting in that direction? And we have various industry studies and surveys that help us understand this. You see on the right a particular focus on Amazon customers who cite that the growing customer demand for Amazon is related to cost issues, convenience, the selection available, and access to information in the form of ratings and so on. There's another study that says that 49% of shoppers will want to shop online, I should say, if same-day delivery becomes more prominent, and so that will create part of this surge. And in general, not just for Amazon, but for online customers in general, convenience and free shipping are major factors. So this has created a number of challenges for the industry and for transportation specifically. One that's been getting a lot of attention recently is a shortage of drivers. So a very large fraction of last mile delivery firms say that finding qualified drivers is their biggest issue in North America. And we can kind of appreciate some of the reasons for this related to the concerns of the drive of labor in the context of the pandemic. You see the picture on the right there saying, showing the extreme measures that some companies have taken to recruit drivers, including going outside the human species. So that's one kind of form of congestion, but another form of congestion that's much more close to the kind of center of interest for NICR in our community is road congestion. And the urban parcel delivery is has been found to be a major source of the congestion problem in the U.S. There is one estimate that delivery trucks create about 11% of the nation's congestion cost. One particular anecdote is that in Seattle, 28% of the time that vehicle drivers are working, they're spending their time searching for parking. And of course, one offset of that, which has a direct implication for the congestion impact, is that sometimes instead of completing their search and finding regular parking, they instead do engage in double parking, which creates bottlenecks and which will be a major focus of our subsequent discussion. So one thing that when I was getting into this topic, one thing that I wondered about was what is the kind of net impact of the last mile delivery traffic? And there has been some work that has looked at that, and this is the results of that. So we imagine that we have 100%, the top bar here is all the last mile delivery traffic directly. So if we just count delivery vehicles on the road, that would be 100%. So that's one piece. There's a bit of a additional induced traffic because not all the last mile deliveries are directly to the doorstep. So some last mile deliveries entail some other traffic as recipients go to pick up the parcels, say from parcel lockers. On the other hand, as we saw before, last mile delivery is competing directly with offline commerce. So there is a slight offsetting effect of reduced commercial traffic in terms of deliveries to stores. These last two effects are quite small numbers, 2% increase and a 1% decrease respectively. And then the big one, the one that I thought might be even bigger, was that people are making fewer trips to the stores. So one might think, well, just simplistically, for every delivery trip, that kind of displaces a trip from the consumer to a store, but that's not really the case. So by about 32%, there's a kind of a 32% rebound, if you will, resulting from fewer individual trips to the store. But in the end, the bottom line is that about 70% of the last mile delivery traffic that we see is actual kind of a net increase, taking into account all these knock-on effects and displacement effects into that calculation. So this has impacts on land use and building types. In general, it's changing our world in many ways. So there's been vast increases in the land devoted to e-commerce in the form of new fulfillment centers, sortation centers, delivery stations, regional air hubs, etc. Just in 2020 alone, Amazon alone created 175 of these new facilities. It has also affected employment, not just in the context of drivers, but other kinds of workers that work in these new facilities, and basically a shift in employment from traditional offline retail, such as checkout people, for example, and moving towards people working in these big fulfillment centers. And there has been also, and is anticipated to be more substantial impact on the environment in terms of just more delivery vehicles, greater emissions, and again, closest to our interest here, greater congestion. So this is another study that is suggesting that as the result of package delivery, there'll be a 21% or 11-minute increase in the average commute time because of the congestion that is caused by these delivery activities. And as you see on the bars on the right side, a good chunk of that, the majority of that in 2030 is last mile induced and as opposed to line haul induced. So this sort of sets up the problem that we're addressing here, and many researchers and entrepreneurs and others are engaged in mitigating the issues that we've talked about, including new classes of delivery vehicles, particularly electric vehicles that are more environmentally friendly. Also other kinds of operations using sort of multimodal approaches. One of the focuses in our discussion later, in fact, the primary focus will be drones, but other potential solutions involve cargo bikes, autonomous robots, and one of my former students and a colleague, Bozu, has been working a lot on this crowd shipping. So there is a whole industry around people that serve as kind of like the Uber drivers of last mile delivery. So they make themselves available for bicycle or pedestrian deliveries, and there are apps that are set up to enable that to happen. Another approach to mitigating congestion revolves around better logistics, basically trying to cut delivery times and emissions levels by having routing of vehicles that is more efficient and basically reduces the amount of overall vehicle miles that must be accomplished to make a certain set of delivery activities. Some of these are kind of classical vehicle routing problems that have been studied for a very long time, but are being repurposed for this particular issue. There are other more novel approaches that involve, say, combining a surface vehicle with drones. So the drones become kind of like a force multiplier for the surface vehicle. The driver drives a regular route, but when they make stops to make their own deliveries, they're also deploying drones to make other deliveries. So instead of one delivery per surface vehicle stop, there can be several via these drones that are accompanying the vehicle. So that is all kind of big picture stuff. The next thing that I will be talking about is focusing specifically on the impact of delivery service operations on urban congestion using a technique known as the macroscopic fundamental diagram. So let me just say a little bit about that. First, sort of the background of why we're using the MFD in this context. So we'll be using this term delivery service provider to by this we mean these last mile deliveries. And we want to see the effect of these DSPs on traffic outcomes, including vehicle miles traveled, delay, and air pollution. And our ways in which this can happen qualitatively include just additional traffic on the system, so additional vehicle miles traveled, and then parking. So even assuming that a DSP vehicle parks off the system, that parks does not double park, they are still using parking spaces that might otherwise be used by others, who then have to look more for parking spaces themselves. And then finally, the major focus here is double parking, where a delivery vehicle double parks because they are unable to find a regular parking space. And this is probably the single biggest impact of DSPs on congestion and delay and pollution. So to understand what that impact is, we make use of a very increasingly popular paradigm for understanding urban traffic. That is the macroscopic fundamental diagram. And so this is lifted directly from a paper, a recent paper that looks at these MFDs and documents the phenomenon that they capture. So if you look particularly on, Stephanie, I just did something by mistake. Let's see if I can.
Oh, no,
Did I do that?
I'm trying to get it. I think so. That's okay. I'll fix it. Please hold tight, guys. We're working on it. Remember what slide we
Do you want me to
on,
just maybe I can just bond through it?
Yeah, that's good.
Hold on, my mouse is reacting. Okay, so this is, I see what I'm doing. My mouse keeps accidentally clicking, so I have to keep it away from those arrows. So if we look on the bottom two figures here, we imagine that there is a regional network, which is kind of a part of a city that is fairly homogeneous in terms of the properties of its road network. And we imagine in this part of the city, we measure different quantities. One thing we can measure is the accumulation, which is just the number of vehicles that are on that network at a given time. And the another thing that we can measure is on the vertical axis, and that is production. And that is basically the number of vehicle kilometers per hour. So it's similar to a flow for a single link, but it's looking at an entire regional network. And associated with the plot on the lower left is the one on the lower right, which shows that the effect of accumulation on the average speed of the vehicles. So that particular result was for a particular city, Zurich, but we see similar results in other cities, and these are from another paper that documents this macroscopic fundamental diagram in networks in Nairobi and San Francisco and Yokohama. So now what does this have to do with the delivery activity? So we're focusing here on the effect of double parking on the MFD. And if you look on the figure on the left here, we see two macroscopic fundamental diagrams. The first one is kind of a baseline that we would see in the absence of double parking. And the second one, the lower one, is the macroscopic fundamental diagram that would result from the double parking of vehicles. We see some dots there, and the green dots represent a case where, as a result of the double parking, we have marginally lower productivity in the network, but it's not any kind of sort of catastrophic effect. We have slightly more occupancy and slightly lower flow with the green dots. Our particular concern is more with the red dots, where in the initial red dot, without the double parking, we're kind of just at the capacity of the network before it goes into its downward sloping regime. But then, as a result of the double parking, that kind of puts it into this downward sloping part of the MFD. And without traffic control, the result of the lower vehicle miles with increasing vehicles vehicles continuing to enter into the system and accumulation growing, therefore, is that we could get a very drastic effect on congestion. If so, the combination of double parking and not controlling the flow of vehicles into the part of the city that we're looking at can result in this very substantial effect that translates into an impact on speed, and it also translates to an impact on delay. So our work based on this kind of notion is to see if we can model this in a fairly simple way. And so we developed an extremely simple theoretical model, which is at the bottom bullet here, which basically is looking at a way of predicting how double parking will affect the capacity of a regional network, such as the ones we were just analyzing. And we see that it depends on a simple metric called delta, which is the average proportion of the time a double parked vehicle is present on a given link of the network. And so we did the red dashed line represents the predictions of this very simple theoretical model. And then we validated that model using a macroscopic network simulation known as AIM-SUM. So this simulates traffic in a microscopic way and yields basically points on that macroscopic fundamental diagram based on the simulation. And if you compare the black dots and the red dashed line, you can see that the very simple model provides quite good approximation of what the microscopic fundamental diagram would suggest. And both the model and the simulation results show that having, as we increase the number of stock vehicles on a link, that greatly affects the average network capacity. This also affects air pollution because of the relationship between various emission rates. Here we focused on CO2 emissions and speed. And so I am going to stop here, and then the next part of our talk, Lee will present, and it will involve the potential role of UAV-based parcel deliveries as a solution to this problem, and look at the issues of the potential congestion in the skies that could result if we tried to use this solution at scale. Go ahead, An.
Thank you, Mark. Can you guys hear me well? Can we hear me?
Yes, I can hear you.
Okay, that's great. We have seen a large impact of increasing urban parcel delivery demand on traffic congestion. To mitigate the congestion, one way is to shift the ground delivery demand to the air, where packages are delivered by UAVs. We would like to see the possibility of having a scalable case operation that surface vehicle trips are replaced by UAV delivery in the air. In the following presentation, I will talk about our UAV traffic management framework and how it performs under a large delivery. UAV delivery could have several advantages, such as reducing ground traffic, shorter delivery times, and lower maintenance costs. In the last few years, many large organizations started using drones in package delivery. In 2019, FedEx Express and Wing Aviation have completed the U.S. first scheduled commercial residential drone delivery. UPS and Amazon also got FAA approval for drone delivery in 2019. Path planning is important in drone delivery system to identify efficient and safe flight trajectories in a timely manner, so that UAVs can accomplish their missions and avoid obstacles. A lot of research apply different path planning algorithms to UAV routing, including A-star. Hello? Okay. A lot of research applied different path planning algorithms to UAV routing, including A-star with JPS, RSR, and other routing algorithms like RRT's optimal control and fast marching algorithms. As UAV technology and civil applications have emerged over the past decade, several countries have undertaken efforts to develop UTM, UAS traffic management. Organizations including NASA, NICR in Netherlands, also other organizations from Singapore, Korea, have undertaken the task of developing traffic management methods for UAV operations. There are some potential risks of using new class of vehicles, including UAV, for parcel delivery, including noise drop packages. Though there are some solutions to these issues, like geofencing, safety distance, and so on, this is not the focus of our research. In our research, we take San Francisco as case study and study the case of moving around 20% of surface delivery trips to UAV deliveries to reduce the ground delivery traffic. According to USPS delivery data, around 750,000 packages are delivered in a week in San Francisco in December 2019, which is about 100,000 packages a day. We assume a 10-hour daily delivery window. This amounts 5,000 packages per 30 minutes. We work on the 1,000 package per 30 minutes case in our work, which is equivalent to moving around 20% of the traffic to the air. We assume a linear relationship between delivery demand generation and building height. Then we generate the origin and destination points based on the building height, such that the distance between origin and destination is between 1,000 meters and 10,000 meters. In existing literatures, there are limited research on integrating UTM for parcel delivery, and there is little study concerned with identifying and efficiently resolving path conflicts in a UAV system that features the high traffic intensity and may be required to relieve road congestion or reduce pandemic threat. The goal of this work is to propose a framework of a UAV system traffic management, including UAV path planning, UAS traffic management, and mechanism design for resource allocation. We are also going to assess the ability of the proposed framework to handle the 20% ground delivery demand shifted to the air. Our methodology includes 3 components required to simulate and evaluate the proposed strategic UAS traffic management, including UAV path planning for the first part, then UAS traffic management. The second part includes a conflict detection and strategic conflict resolution. Third, since efficient conflict resolution requires truthful information about flight operator preferences, we design a mechanism that induces truthful information reporting by UAS operators through a payment scheme. We first proposed a deterministic clustering-based single UAV path planning algorithm. For given OD, we simplify the 3D routing to 2D horizontal routing at different altitudes. Since we're not considering any uncertainty at current stage, we assume that all UAV flights will ascend at origin, travel horizontally at certain altitude, and descend at destination. Under this setting, a key trade-off of UAV flight path is that low altitude path, shown in the path 2, will tend to be longer because there are more obstacles to be avoided, whereas high altitude path, which is path 1 in the right graph, while shorter, involve greater costs for ascent and descent. Then we are able to determine the optimal travel altitude for a given UAV mission by minimizing a linear cost function associated with both horizontal and vertical flying. There are two steps for our UAV path planning. The first step is to perform clustering on fixed obstacles in the city. We can generate representative altitudes as the maximum height of buildings within each cluster. Second step is to perform shortest path algorithm to generate horizontal travel path at every altitude candidate. We can calculate total travel cost, including horizontal path and ascent and descent parts over all altitude candidates. The optimal path and altitude are the case with least total cost. We show the elevation grid map of all static obstacles, including geographic and above-ground obstacles. Both coordinates and obstacle elevation are used as clustering features. The right figure shows the obstacle clustering results. We can see that Twin Peaks and San Bruno mountain area have the highest elevation. It is also interesting to see that around here, a lot of green dots are clustered together as in one group. Those are the commercial areas of San Francisco near Market Street and corresponding to the high-rise buildings in the CBD area. So we got both the cluster of obstacles and cluster altitudes from the results. We also show the results of horizontal shortest path at 6 altitudes for the same OD pair by saturated vast margin square algorithm. You may notice from left to right, from first row to second, when the flight is traveling at lower altitude, the horizontal shortest path is longer. The optimal path and altitude are determined as one with the least total cost. We also use the same way to generate the path with second least total cost as our alternative path for rerouting in later work. The second part is UAS traffic management for parcel delivery. We present a range of traffic management models with varying sophistication. Each model aims to efficiently schedule and route each UAV flight while resolving UAV path conflicts. The alternative models, in order of simplicity, are the sequential delay model, sequential delay reroute model, full optimization model, and batch optimization model. We start by detecting flight pairs whose candidate paths create a spatial conflict. A spatial conflict is also a temporal conflict if there would be simultaneous occupancy of the conflict region based on the desired departure times of 2 conflict flights. The temporal conflicts must be resolved by means of either departure delay or an alternative path. Traffic management models will decide how to assign delay or to reroute flights to resolve those temporal conflicts. Our first model is SD model. The SD model assigns flights a priority order and resolve a conflict between 2 flights by delaying the flight with lower priority. A desirable feature of the model is that it requires no inputs other than the desired routes and the flight sequence. For example, when we decide on the departure time for flight 5, which have priority 3, we are showing here, and we will assign the earliest possible time that avoid to be in the conflict region with flight 2 and flight 4, which have the higher priority. We show the possible cases that flights may occupy the conflict region along the time axis. In case 2, flight 5 and flight 2 have simultaneous occupancy of conflict region 1. Certain delay will be applied to flight 5 to wait until flight 2 exits the conflict region. We need to carefully deconflict with all higher priority flights, since the conflict with one flight may cause new conflict with another flight. In case 3, deconflict flight 5 with flight 4 cause new conflict between flight 5 and flight 2. Our SD model considers all the possible cases of those conflict situations. And our second model is SDR model. SDR model is also based on the flight priority, but may resolve a conflict either by delaying a flight or assigning a flight a different path, or possibly both. This model requires UAV operators to submit cost information so that the operator can choose the conflict resolution strategy with the least cost. The rest 2 models are optimization models. In contrast to the sequential models, the optimization model assigns delay and path in order to minimize the total cost of eliminating all conflicts. For this model, the operator requires additional cost information for each UAV mission. Further, to assure that operators provide truthful information, the optimization models must be paired with a mechanism design that is incentive compatible. So how does the full optimization model work? Basically, the FO model takes following inputs: recognized spatial conflict pairs, desired departure time and path, and flight information. It will assign new departure time and path to UAVs and resolve all the conflicts and minimize the system total cost. Our full optimization model is formulated as mixed integer linear program. We have delay cost and path cost as our minimization objective function. Conflict resolution by either delay or reroute are embedded in the constraints. The FO model gives us a much better schedule results than SD and SDR model. However, the FO model is computationally intensive when traffic density is high. This motivates a variant of the model which assigns flights in batches so that most conflicts are between flights in the same batch. Flight conflicts between batches are resolved sequentially based on batch priority. We will show later that BO model will yield still very high quality solution while running much faster than the FO model. First, we want to assign flights to different batches where flight conflicts are mostly within batch instead of between different batches. We do this through network analysis technique. We design a weighted node and link network where each node represents a flight. Two flights are connected by an edge if there exists a spatial conflict between them. Then a moving method of community detection is performed on the network to generate different batches of flights. We assign a priority order to each flight group and incrementally optimize the routes and schedules of each flight group based on the group priority order. For each flight group, we will both deconflict flights in the same flight group and flights in a higher priority group. We are going to show our model results. Since the FO model is very computationally expensive with high traffic intensity, we compare all four models using a smaller case with 200 flights. The comparison results is not shown here, but we prove that BO model yields a suboptimal results than FO model, but the penalty is modest. The BO model has very close performance to FO model. Here we show the results of SD, SDR, and BO model of 1,000 flights in 30-minute case. In the left table, the BO model generates schedules with a system cost that is significantly lower. It is interesting to see that BO and SDR model have much less congestion cost than SD model. In the cumulative diagram on the right, BO model and SDR model are much closer to the plot of scheduled departure time than the SD model. In the SD model, UAV traffic is saturated. Many flights are delayed to depart after the end of the 30-minute period. Note that this is only a 30-minute time period, and at the end of the day of the operation, we can expect many delayed flights by SD model will pile up, but other models can handle the traffic much better than SDR model. The third part of the work is the design of a mechanism that induces truthful information reporting by UAS operators through a payment scheme. In our mechanism of traffic management, the central controller has information on unit delay cost and path cost of all UAV flights. This gives a rise to the issue that whether the information reported from each UAV operator is truthful, as an UAV flight may deliberately misreport information to get a more favorable route or lower delay. The issue can be addressed by adapting the VCG mechanism to the UAS traffic management context. We calculate the payment of 1,000 UAV flights using BO model. The first figure is our payment distribution. About half of the flights have zero or very small payment. Fewer flights have higher payments. We use the different colors to denote the payment of 1,000 flights along with their path at 7 altitudes in other figures in this slide. Conceptually, a flight with more conflicts tend to impose more externalities on other flights, thereby incurring more payment. Altitudes with fewer UAV flight, such as the 46 meters here in the highest altitude of 264 meters, tend to have lower payment range. More flights at an altitude contribute to more conflicts and higher payments. For conclusion, the MFD model, the macroscopic fundamental diagram model, developed from this research is sensitive to urban delivery activities. And the MFD model can assess how current delivery activities contribute to urban congestion and how the alternative delivery activities alleviate the traffic congestion in urban areas. In the UAV traffic management part, the UAV path planning algorithm takes advantage of clustering obstacles to generate representative altitude candidates, which is more efficient than the evenly spaced altitudes assumed in most previous research of UAV system planning and analysis. In determining the optimal travel path, the trade-off between horizontal shortest path length and vertical travel distance at different altitudes is recognized. Among 4 traffic management models, we find that the BO model, which can solve large-scale problems in short time, while making a slight compromise on solution optimality, is more attractive than the FO and SDR models to solve the large-size problems. Finally, we find that the payment made by a UAV flight increases with traffic intensity and the extent of interactions a flight has with other flights. For future research, to mitigate the congestion impact from truck traffic, as well as reduce costs and travel times, last mile delivery should in many cases be shifted toward UAV and non-motorized modes, including cargo bikes. We are interested in developing a suite of multimodal congestion-sensitive strategies for urban delivery by integrating traditional motorized vehicles, non-motorized vehicles, and UAV. Previous research focuses on modeling and managing urban road congestion and logistics studies for UAV route optimization and scheduling. In our future work, we will focus on new models that combine various modes for integrated and coordinated urban package delivery. Also, we will evaluate the congestion mitigation using macroscopic fundamental diagram with multimodal last-mile delivery strategies. Thank you so much. We are very happy to take any question. I'll hand it over to Stephanie.
Thank you so much, Mark and Ange, for the great presentation and all the wonderful information. What I'm going to do now is we've got about 9 minutes or so for questions. I would like to just simply remind everybody that the Q&A box is located on the bottom right-hand corner of your screen. Simply type in any questions and or comments that you had, or have, I should say, and we'll get to all of those questions. And it seems like we do have several questions already in queue, so we'll get to them one at a time. So please be patient as we work our way through all the questions that have been submitted. The first question comes in, and I don't know if this is for you or for Mark, but it says, is the airspace discretized into grids when planning flight paths?
Okay. In the UAV traffic management part, the airspace is not discretized into grids. We just assume the free mix of the airspace. The UAV flight can fly anywhere they want. They just for the path planning part, we're just directly generating the shortest path without discretizing the airspace. Does that answer the?
Thank you. Yeah, I think that does answer the question. The next question comes in. It says, for batch optimization model, how did you decide the priority, and what solver are you using?
So for the batch optimization model, the group priority order, we tried several metrics to assign the priority, including the sum of degree centrality within a cluster, the average scheduled departure time of the cluster, and the cost increase of a cluster. And it turns out that the sum of degree centrality within a cluster performs the best. So we use that to assign the group priority order for the batch optimization model. And for the optimization model, the solver, I used CFlex to solve the model.
Thank you. We do have a comment before this next question. It comes in and says, great presentation, wonderful work. And then the question follows up and says, what's the energy implication if we switch the ground transportation to air?
Okay, so for the energy implication, I'm not very sure if I understand it correctly, but since the UAV traffic management part is not considering the energy consumption for UAVs when it's still when we're assigning the schedules, so I'm not sure like how much energy consumption for that part like will be different after shifting the traffic from ground to the air. But we do consider, we add a buffer of the UAV to reach its charging station like after the delivery trip. So that's why we will limit the OD trip in our study from 1,000 meters to 10,000 meters, because the 10,000 meters is kind of an upper limit travel distance with around 10 to 20% battery left for the UAV to reach its next charging point. I don't know if I answered the question correctly. I don't know if the answer is what you want, but there is definitely other studies in the literatures. They do the schedulings of UAV parcel deliveries considering the batteries and the limit of traveling in the scheduling optimization models. There's definitely other literatures working on that.
Can I add a couple comments?
Yeah, sure.
So firstly, these vehicles will be electric vehicles, which Ang implied, but that obviously has implications for energy. The other thing that people have observed is that if we think of a classic surface vehicle delivery and think of the amount, the weight of the vehicle compared to the weight of what's being delivered, there's a huge amount of kind of wasted energy in terms of just moving this heavy vehicle around. And UAVs are much, much lighter. So the sort of ratio of payload to vehicle weight is much greater. So I think there are certainly reasons to be optimistic about the energy implications, but it's not something that we've looked at in depth.
Thank you, Mark. There again, comment that it was a great presentation, and then a follow-up, or there was a question that followed that statement was, have you looked into truck plus UAV format? So, for example, trucks carrying the UAVs along the main delivery routes, and UAVs taking care of truck to door delivery and then going back to the truck.
Oh, that's a good point. So from our current presented research, we're not considering the truck plus UAV format. We're only working on the traffic management for UAVs only for parcel delivery. But in our next stage of research, we are considering to do a traffic management for the multi-modal parcel delivery that will include both truck UAVs and other non-motorized vehicles like cargo bikes. But there's definitely a well-studied area called vehicle routing problems with drones that studies a lot about having trucks go traveling the main delivery routes and UAVs will delivery to the doorstep. But for our next stage, we will not focus on the vehicle routing problem, but in a congestion context for the multi-modal delivery.
Okay. Thank you, Ang and Mark, so much for the great presentation. We do have a couple minutes left, so what I wanted to do now was I will open up the evaluation for everybody on your end. If you could take a few moments to complete that evaluation, as the feedback provided is not only important to our presenters today, but the entire NICR webcast series. And if you have a speaker or a topic that you would like to hear a little bit more about or from, please include that in number 6 in the evaluation. Our next webinar is scheduled for December 2nd, so that's a little bit less than a month away. I've also dropped a quick link to that webinar in the web link section that is listed as number 8. We will be discussing Enhancing Equity and Access, the case of e-scooters in Mayagüez, Puerto Rico, from our research partner. So again, thank you so much for attending today's webinar, and we'll see you in December. Bye, everybody.
Bye. Thank you.
Thank you.
You're welcome. Thank you.